In this video, we'll be covering the principles of setting up a basic robot machining cell using Machine Maker, which is available with every installation of ENCY, and it can be found by clicking on the 3-bar utility icon up in the top left of the screen here, and then clicking on Machine Maker, which will open it in a subsequent window. So, as you can see, we're starting from a completely blank canvas here. And to add the first element, which is going to be a robotic arm, I'm going to click on the machine library here, mechanisms library, sorry, which is a complete listing of everything that you have installed locally, but also gives you access to a very, very well stocked online repository of parts that have already been set up and exhaustively tested and proven to work by the team at ENCY, which makes our lives an awful lot easier. So to install a robot arm, I'm going to click on Robot, and since it's a very, very common and popular unit, I'm going to type in KR210 because it's, as I say, it's a KUKA robot that appears almost everywhere. I'll click on Add now, and you can see we now have our instantly installed KUKA KR210 robot. However, as nice as this is, it's not much use to us without an end effector. So we're now going to add an end effector by clearing the search results, going to the end effector subset, and for the sake of this particular illustration, I'm going to click on the bottom techno motor end effector, which is again a fairly common spindle motor, and I'll click on Add. So you can see that automatically it's applied it to the end of the end effector flange on the robot. This is obviously very helpful and appropriate linkage and everything. However, it doesn't account for things like any kind of mounting plates that are going to be present, so we need to adjust that ourselves. So to do so, we click back in the main space. I'm going to click front on the navigation cube, so we've got a nice perpendicular view of the surfaces we need. And then I'm going to double click on the spindle motor itself. I'm going to ignore what's in here for the moment, and we're going to go to the model tab because that's more immediately useful. I'm going to zoom in by scrolling our mouse wheel down a little bit. Now, I want to move this away from the flange plate a little bit because obviously there's going to be some kind of interface plate that's used to bolt everything together. And I am going to move it by 20 millimeters, which, sure, it's a bit overkill in real world situations, but it's a nice clear illustration of what we're doing here. Now, the thing to note is because that motion is predicated on the flange plate's position and orientation in space, we need to move the spindle motor in Z, not in X, as one would initially suspect. So in the number boxes down here under Move and under Z, I'm going to type in at 20. And you can see how that's now moved in the direction that we're expecting it to. And I'm going to click on Apply. There is, however, still a slight problem that needs addressing with this. And if we zoom back in, you can see that the TCP point is now offset from the rest of the spindle. Now, ordinarily, you would determine the TCP location and position by running a twin spike calibration method or whatever. But for the sake of simple alignment in this, because we're only doing a demo cell here, I'm going to double click on the spindle again, and in the TCP setting I'm just going to bump up the Z value by 20. So 105 brings the TCP back in line with where the spindle nose actually is. However, for the sake of accurate settings of TCPs, the team at ENCY have actually gone and put together a mobile phone app which will make your life a lot easier when doing this. So instead of having to scribble down some very, very long and detailed numbers with tiny, tiny decimal values hanging off the end of them, you can actually just take a photograph of the TCP results in the Machine Maker app on your phone, and it will transcribe those results for you. It will also list the tool length, so it'll make the necessary transformation for those results. And you can then use that same app to photograph this QR code, and it will automatically transfer those results for you without any possibility of there being a mistyped number or an accidental slip of a decimal place or whatever, which, let's be honest, we've all done it before. which will save you a lot of potential pain when setting up your robot for yourself. It's a really, really useful feature, and one that's absolutely worth downloading from either the Apple App Store or the Android Play Store, depending upon your platform of choice. Anyway, we've now set this, so we click on Apply to close that out again. So great, we've got our robot, we've got our spindle. Let's say we want to add a turntable now as well. So to do this, I'm going to go back to the Mechanisms library, and I am going to click on Table. And we now have a very nice, very comprehensive listing of single and dual axis turntables of various configurations and orientations, as well as some static tables as well. For this, I am just going to click on a very, very simple known entity, the KP1V500 turntable. Again, KUKA product, matches the arm nicely, and they're pretty ubiquitous. So I click on Add. Now we can see that it's been set up in a place that's not very useful to us. So instead of leaving it as is, we've got a couple of options to be able to move it around. The first being we can just click on it to highlight it, hold Control, and then drag it around the environment. This doesn't really give us the level of precision that we're going to need though, because as we're all well aware, precision is very much the name of the game when it comes to setting up robots. So instead, with this still highlighted, we're going to go into the numerical data points here. I'm going to type in, say, 1950 in X and minus 320 in Y. I'm going to leave the Z value alone because unless your turntable is recessed into the ground or is of a drastically different height than the pre-configured models here, like it's on a plinth, for example, it is a very, very dangerous move to change the Z value, because that Z is predicated on the top surface plane of the turntable itself, and that defines the user coordinate system for being able to machine objects on said turntable. So if, for example, I were to type in 700 instead of 705, and it turns out that the real world turntable is not recessed 5mm into the floor, you're going to potentially be taking 5mm of steel off the turntable plate, which at the kind of speeds that robots tend to machine at, that's not going to go well for anyone. Anyway, now that we have our basic machining cell set up, we can go through the process of simulating the range of motions, so we've got a clear idea as to where any kind of restrictions need to be imposed. And we have a very handy tool for that within Machine Maker itself. So if you click on the Run Simulation icon here, you will have the option to not only enable collision detection, which I'm going to click in a second, but you can also demonstrate the ranges of motion available to us using these particular kinematic structures. So I'm going to click on Enable Collisions Detection now. It will take a few seconds for it to calculate what it's doing. Okay, so now that that's fully calculated, we'll start out with trialing the turntable range of motion first. So we'll click on Demo here, and we can see the turntable rotating through both 180-degree ranges of motion for it. Now, if we click on Demo for the robot arm, we will see a few collisions coming up, because obviously it hasn't accounted for the length of the spindle yet, and there's a fair chance that when it leans forward, it may hit the turntable. But since this is just a very, very fast demonstration of the entire range of motion, we can then subsequently go back and take a look at what ranges we have to limit it to and what we can't allow it to go near. It's a very, very